Pluto is a far-off and baffling dwarf planet that was once a member of our solar system's planetary family. However, recent shocking announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning discovery. They suggest that this cold world is on a potential impact course with Neptune. But how could this happen, and what might be the consequences of such an enormous event? Are we witnessing a rare galactic phenomenon, or is there more to this looming cosmic impact? Join us as we explore the possibilities of a Pluto-Neptune collision. Pluto, a former planet downgraded to a dwarf planet partly because of its peculiar orbit, remains a subject of interest and study in the astronomical community. According to recent predictions by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential hazardous collision between these two celestial bodies, which could pose a massive threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution yet. But the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the near-circular orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination, tilted at 17 degrees to the ecliptic plane. The path Pluto follows is much steeper compared to other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's path. For around 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, a contradiction to what we might expect from their positions in the solar system. This leads to the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers sought to understand its unique trajectory. Unlike other planets whose orbits lie mostly near the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricacies of orbital mechanics. The three-body problem in space involves understanding how three objects, such as Pluto, Neptune, and the Sun, move and influence one another with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this issue demonstrates how its path, Neptune's path, and the Sun's gravity all work together in a complex way. Terms like azimuthal libration and zonal libration, along with the VZK oscillation, are crucial to solving this puzzle. According to astrophysicists, what keeps all planets in their orbits is azimuthal libration. For Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is critical in preventing their paths from intersecting. Zonal libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned significantly above their orbital plane, providing an additional layer of safety from potential collisions. Another crucial factor in this scenario is the VZK oscillation, named after scientists who studied how objects move in space. It involves the way three celestial objects like Pluto, Neptune, and the Sun interact gravitationally. This oscillation explains why Pluto's path around the Sun is so unusual. Despite its seemingly erratic trajectory, this oscillation helps keep Pluto moving smoothly over long periods. The VZK oscillation shows that, even when space objects appear chaotic, certain patterns and rules maintain order. These dynamics help keep Pluto's orbit stable, ensuring it neither collides with Neptune nor veers off course. This three-body problem is key to understanding how orbits evolve due to gravitational interactions between celestial bodies. Studying it not only helps us learn about Pluto and our solar system but also about distant worlds and their stars. Numerical simulations in the late 1980s revealed that, despite these stabilizing properties, Pluto's orbit is technically chaotic. Minor deviations in initial conditions can lead to significant differences over thousands of years. However, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the chaos in check. Recent computer simulations have helped scientists understand how the giant planets, like Neptune, Jupiter, and Saturn, affect Pluto's path around the Sun. Neptune has a special relationship with Pluto. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's path stable. But Neptune isn't the only planet playing a role. Jupiter's gravity also significantly contributes to Pluto's orbital stability, and Saturn provides additional support as well. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto remains on a stable trajectory for a very long time, even billions of years. It's as though Neptune, Jupiter, and Saturn are working together to ensure Pluto continues moving safely through space without encountering trouble. These phenomena are essential for maintaining order and consistency in the solar system. Without them, the solar system would be a far more chaotic and unpredictable place. Bodies like Pluto could collide with others or be ejected from their orbits, creating a domino effect on other celestial bodies. For Pluto, especially with discussions about its potential collision with Neptune in the future, understanding its orbit is crucial. This gives a clearer picture of the solar system's dynamic nature. The case of Pluto demonstrates how even the most seemingly unstable orbits can achieve a state of balance through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and analysis of these phenomena to better understand our place in the universe. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's path on its initial conditions, is vividly demonstrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or velocity can significantly alter its long-term orbit. Using computational simulations has been immensely helpful for scientists in unraveling how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other celestial objects, like Neptune, interact gravitationally. By tweaking small details in the simulations, astronomers can better understand Pluto's behavior, how even little changes can have a major effect. In the last part of the 1980s, these reproductions showed something fascinating about Pluto's orbit. Despite the fact that it has features like AIML and scope libration to keep it consistent, its trajectory can still be wild and capricious. If you start with only a minuscule difference in where Pluto is or how fast it's moving, its path can end up looking completely different over many years. Yet, even with this chaos, Pluto's orbit remains stable for a very long time, billions of years. This means that Pluto's journey around the Sun has a sort of order to it, despite seeming chaotic at first. Predicting cosmic events, especially when they involve chaotic orbits like Pluto's, is a significant challenge. The inherent unpredictability of these systems means that long-term forecasts are often fraught with uncertainties. While numerical simulations provide powerful tools to understand and anticipate the future paths of celestial bodies, they also highlight the limits of our predictive capabilities. These models depend heavily on the accuracy of initial conditions, and any slight error or misrepresentation can lead to vastly different outcomes, making precise predictions a daunting task. Moreover, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made significant strides in understanding space, Pluto's case reminds us how much of our knowledge about the universe remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have far-reaching effects, influencing the stability and trajectory of other bodies within the system. So, why are significant astrophysicists just now raising concerns about a potential collision between Pluto and Neptune, despite all these complex forces working to prevent such an event? Neil deGrasse Tyson, a prominent astrophysicist and a key figure in popularizing cosmology, offers a unique perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Tyson, known for his role in the reclassification of Pluto from a planet to a dwarf planet, provides insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the unknown realms of space. Tyson's stance on Pluto's reclassification is rooted in the ever-expanding knowledge of our solar system. He sees the reclassification not as a demotion but as a necessary adaptation to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He views the complexities of orbits, such as Pluto's, as a reminder of how much there is still to discover in space. According to Tyson, the fascination with these unknown knowns makes astronomy so captivating. Moreover, Tyson understands how space events and discoveries shape public opinion. His statements on Pluto and Neptune reflect not only his grasp of the public's ongoing interest in space, but also his belief that new knowledge brings new mysteries. But what is his take on the potential for a collision? Tyson suggests that, given the stability of Pluto's orbit over vast timescales, the chances of a catastrophic collision with Neptune are exceedingly small. However, as Tyson has repeatedly emphasized, the universe is a dynamic, evolving system. Even the smallest change in conditions could, over long periods, alter the trajectory of Pluto and other objects within our solar system. Therefore, while a collision may not be an immediate concern, it serves as a fascinating topic for further study and speculation. As we continue to explore the relationship between Pluto and Neptune, it's essential to delve deeper into the role that the Sun and other planets play in stabilizing Pluto's orbit. The solar system operates as a dynamic system where each planet's gravitational influence can affect the trajectories of others. For Pluto, the Sun's immense gravitational pull is the primary force that keeps it bound in orbit. However, Pluto's interactions with Neptune and the other giant planets, such as Jupiter and Saturn, add additional complexities that maintain its peculiar yet stable orbit. Jupiter, the largest planet in the solar system, has a significant effect on Pluto. Its gravity helps dampen any potential orbital disruptions that could occur due to the gravitational pull of Neptune or other distant bodies. This is a crucial point because, without Jupiter's stabilizing influence, the risk of Pluto being ejected from its current orbit or sent into a more erratic path would be much higher. The way Jupiter's gravity interacts with the orbits of other distant objects, including Pluto, has been a subject of intense study for astronomers, as it provides insight into how larger bodies can influence the stability of smaller objects in the solar system. Saturn, although less influential than Jupiter, also contributes to the long-term stability of Pluto's orbit. Both Saturn and Jupiter act as cosmic guardians, ensuring that the smaller, more distant bodies in the outer reaches of the solar system, like Pluto, remain on their predicted paths. The concept of orbital resonance also plays a key role in explaining why Pluto and Neptune don't collide, despite their orbits crossing. The resonance between the two bodies is a sort of gravitational dance, where Pluto's orbit is synchronized with Neptune's in a way that ensures they never occupy the same position in space at the same time. The 2:3 orbital resonance between Pluto and Neptune means that for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance effectively keeps the two bodies from ever getting too close, as their orbits are spaced in such a way that keeps them at a safe distance. Interestingly, the resonance between Pluto and Neptune is not unique in the solar system. Many other objects in the Kuiper Belt, a region of the solar system beyond Neptune populated by small icy bodies, also exhibit orbital resonances with Neptune. These resonances help maintain the long-term stability of the Kuiper Belt, preventing objects from drifting into orbits that could bring them onto collision courses with the inner planets or the gas giants. The study of these resonances has provided astronomers with valuable insights into the gravitational interactions that shape the structure and stability of the solar system.